So welcome everyone to the 4th Annual Robert F. Davis Distinguished Lecture. My name is Justin Schwartz, and as head of the Department of Material Science and Engineering, I have the distinct honor and pleasure of welcoming you here to this beautiful new venue at NC State and introducing today's event. Before I introduce today's lecture, I'd like to start by saying a few words about the lecture series itself. So the Robert F. Davis Lecture Series was created in 2010, so this is our 4th one, to honor the accomplishments of Professor Davis, an internationally recognized material scientist. Professor Davis received his Bachelor of Science degree in ceramic engineering here at NC State in 1964, and then he returned as an assistant professor in 1972. He remained in our faculty for more than 30 years, including over 25 years as our first Kobe Steel Distinguished Professor. During his tenure at NC State, he received the Alexander Holliday Medal for Excellence and the R.J. Reynolds Tobacco Company Award for Excellence in Teaching, Research, and Extension. These are the highest awards given to NC State faculty by the university and the College of Engineering, respectively. 3 of Professor Davis's NC State PhD students, in fact, have gone on and been honored as distinguished engineering alum of the college. Professor Davis has been frequently recognized nationally and internationally, including election into the National Academy of Engineering. Professor Davis recently established an endowment to ensure the long-term health of this lecture series, and I'm very glad to say that he's here with us today. So please join me in welcoming Dr. Davis and thanking him for his contributions to the Let me now turn to today's distinguished lecturer, Professor Mildred Dresselhaus from the Massachusetts Institute of Technology. Professor Dresselhaus received her undergraduate degree at Hunter College in New York, where she was trained to be a school teacher. After graduation, she received a Fulbright Fellowship to attend the University of Cambridge, and fortunately for all of us, she accepted that, and that's where her interest in physics was really sparked. After Cambridge, she attended the University of Chicago, where she conducted research in superconductivity and received her PhD in 1958. After postgraduate studies at Harvard and Cornell, she moved to Lincoln Lab as a staff member, and in 1967, she became a visiting professor of electrical engineering at MIT, and a year later, 1968, she became a tenured faculty member. In 1985, she was promoted to institute professor, which is the highest faculty rank possible at MIT. Professor Dresselhaus's awards and honors are really way too far and numerous to mention, so here I'll just give you a few of the highlights. In 1974, she was elected to the National Academy of Engineering, in 1985 to the National Academy of Sciences, and in 1990 she received the National Medal of Science in recognition for her work on electronic properties of materials, as well as for her tremendous efforts in expanding the opportunities for women in science and engineering. She has received the Founders Medal from the IEEE, the Oersted Medal from the American Association of Physics Teachers, the Vannevar Bush Award, the Einstein Professorship from the Chinese Academy of Sciences, and on January 11, 2012, President Obama announced Professor Dresselhaus as a co-recipient of the Enrico Fermi Award. Only 4 months later, in May of 2012, she was awarded the Kavli Prize for her pioneering contributions to the study of phonons, electron-phonon interactions, and thermal transport in nanostructures. She has received 30 honorary doctorates from universities in 10 different countries on 4 different continents. She served as the treasurer of the National Academy of Sciences, the director of the Office of Science at the U.S. Department of Energy, the chair of the governing board of the American Institute of Physics, president of the American Physical Society, president of the American Association for Advancement of Science. She has published over 1,100 journal articles, been cited well over 50,000 times by 30,000 other articles, and for those who follow H-index, it's a staggering 104. Professor Dresselhaus is particularly noted for her work on graphite intercalation compounds, fullerenes, carbon nanotubes, and low-dimensional thermoelectrics. Please join me in welcoming Professor Mildred Dresselhaus to North Carolina State University.
Well, thank you for that introduction. I didn't know those statistics. Really, I'm not too interested in them. I'm still interested more in science than in those statistics. So I'm really happy to have been asked. Great honor to be here. And I entitled my talk, 50-Year Adventure with Nanosciences. So let's see if we can get that up on the board. activate. Thank you. Thank you. So, you'll see here, this is me when I started. So this is me as a postdoc a long, long, long time ago. And this is me today. So close to today. A few months ago. But this year. Okay, so I'm going to tell you about my 50-year adventure in nanoscience. And the good part about it is it's still going on. And I hope that you get the idea that science is kind of forever. And so the first part of my talk, I have a couple of things about nanoscience because I thought I was supposed to do that, tell you what nanoscience is. So nanoscience is about getting smaller and smaller. We can actually start from the large. So the largest that we have in terms of centimeters, I think we're in meters. So meters is 10 to the 25th is as far as we've gone out in space. So our imagination is of how far space goes is 10 to the 25th meters. But where I am, I'm really down in the dumps here at the lowest end, and I work here at tenths of nanometers. Let's see this will work, yeah. So I'm really down even below the bottom of the scale, where we have individual nanotubes, and that's down there. So there's excitement over this whole span. So I have some introductory remarks about the field because I thought that the context might be important. Not everybody in the audience works on materials like I do. So what do we work on anyway? So nanoscience is about fundamental particles, at least for me. So I study electrons. They're carriers of current. But then there are lattice vibrations in every solid there, or material that carries electrons. There are also vibrations. I'm very much interested in that, and we do spectroscopy on that a lot. And the phonons and electrons interact. I'm interested in that, as you heard in my introduction. And we use light to probe this whole thing. You should remember that light is 3 orders of magnitude larger in size in terms of its wavelength than the things we look at. And it's really quite amazing that you can use probes that are so large that are sensitive in some way to the smallness. So I hope that I can convince you that that sort of interaction works and we can learn things from it. So why do we study nanostructured materials? We do so because they're interesting. So why are we interested in them? You take any material X. I heard a lot about iron when I'm going around. We take a nanostructure of iron. It's very different from the bulk. It has different properties. And that's true of every single material out there. Of course, you might think that the highest surface area makes it naturally different because the smaller you get, the more surface area you have toward the number of atoms contained therein. But it's a lot more than that. The science of the nanostructures is different, and I'm going to try to tell you today why it is. And in particular, for some of the things that we study in our lab, we're interested in the independent control of all parameters that can't be done on the macro scale. So we're interested in doing things that couldn't be done otherwise. So that makes it interesting and current. So when you do research, you're always thinking about doing things that people haven't done before, because that's kind of interesting where the frontiers are. You never know if you're going to succeed in doing it. It's always a bit of a gamble. But when you're successful, it's really quite interesting. And the graduate students are very happy to do something new. So, okay, I have a little background here about the challenges of materials research. So this gives you sort of an idea of the bigger picture of materials. So what kind of problems are we thinking about in this era? So these are topics that have been identified in two independent studies, one that I chaired for the National Academy, and another one that was done for the Department of Energy. And they were actually done concurrently with the two study groups not allowed to talk to each other. So these are supposed to be independent studies. The interesting thing is that they came up with many of the same, almost identical identifications of the important topics. So there is some convergence of opinion about what are the topics that are at the forefront of our fields. So the first one is about complex phenomena that emerge that don't come in the individual particles. You have to put them together. So what this means is if you have a sea of electrons, an electron gas, for example, as would occur in a metal, it behaves very differently from the individual electron by itself, because the electrons interact with each other and they also interact with the lattice vibrations. Then there's the whole story of the physics of life. We have biologists in the audience that happen to come to this lecture. This is very much of a forefront field, because we don't know exactly what's the difference between living and inanimate objects, but there is something that's different. The living ones reproduce one another, and so is life in other places in the universe? Probably. We don't know exactly where and what form it takes. That's going to be an interesting thing probably for the future. What happens far from equilibrium and why? That's something we know much more about, and that's a current field of study. Energy demands, that's a very important area, because that we depend on being able to have sustainable energy if future generations will be able to benefit from energy the way we do in our particular lifetimes. Information technology, well, that's all around you. You have your iPhones. We couldn't have imagined iPhones 20 years ago, and here they are. Everybody has them. They walk down the street talking to them. And what discoveries await us at the nano world? And that's going to be mostly the subject of my talk today. So I'll go through this very quickly. So this is out of equilibrium. On this picture, you can see swarms of fish. Swarms of fish behave very differently than an individual one. The galaxies, we have atoms and molecules. They behave very differently than they do it as individuals. We can use this in materials research to make interesting new materials, as you can see on the right-hand side. But out of equilibrium also causes fracture, fatigue, failure, all kind of bad things. So many of these phenomena that we have that are normal and we study have beneficial and not so beneficial aspects. Information technology, the devices have been getting smaller and smaller. We're now at the individual molecule level. And we have devices that actually operating with just a single molecule. They're very interesting. What more can we do at that level? What's next? What's smaller than a single molecule? So that's going to be an interesting thing, is how much smaller we can get with our information technology. And here's the nano world. So the nano world has many different kinds of materials. And my interest has been, at least in recent years, looking at new kinds of materials that we didn't dream about before. But to make this story somewhat coherent, I'll just have one sort of theme line, so and which we'll come to, and this is about nanomaterials, but of a given sort. And here's the picture of the energy demands of the world. You could see us. We were all lit up here in the U.S., right there, all lit up. But there are some dark continents that have not too much. And one of the big challenges of this next 100 years is what's going to happen as the rest of the world develops and also demands the energy at the level that we experience here. How are we going to supply this? The study and the two studies I mentioned cite a number of areas that are growing and current interest. And you could see a list here. The other study has a similar kind of list. Students like to look at these kind of surveys to get ideas. Is this the field I want to get into? Here are some of the things that people are studying now. But maybe there's some things that people in the audience can think of that are not on that list that will become more important. It's always nice to be at the cutting edge, and I'll talk about this. So, catalysts is one way to make materials that you can't think of how to make them, and the chemists come in and give us good ideas. That's not really me. I benefit from all their ideas. Now I'm to my own home ground, which is carbon-based materials, and that's what I've made my 50-year career that I'm talking about today. I worked on other things too, but this is a coherent picture. So in the 1960s, so that's 50 years ago approximately, I was working on graphite. We didn't know what graphite, the electronic structure of graphite was when I got into this. And this plot here is the number of publications per year, and there are very few in this decade. And they're mostly what we tried to do because nobody was interested in this, nobody thought was important. And even my supervisor said, what the heck are you doing working on this? This is not really all that. What is this going to lead to? What are the applications that I didn't really know? But then I got into the nano world in early 1970s. And actually Bell Labs helped me get into the nano world because they asked me the right question. And I got into graphite intercalation compound. And in the 1980s, this vectored into fullerenes. I'll tell you how I got into that, and nanotubes, and graphene, most recently. This thing has been skyrocketing, getting very, very popular. Maybe it's getting too popular now. It's time to get into something else. So, but the European Union has announced a €1 billion program in this area, so they think it's going to keep going for another 10 years. So at least somebody thinks that this is going to be around for a while. So, okay, now I'm going to go fast forward with 50 years of having fun in this field. And so along the way, there have been many graduates. I joined the MIT faculty in 1967, as you heard in the introduction. So my first graduate student to get a degree was 1973, so I call that my beginning. And so we published a paper on this stuff, which is graphite intercalation compound. At that time, we didn't really know how to make nano, but I had the vision, it would be really nice to be able to look at a single sheet of something. And carbon was something that had very weak interlayer bonding. And if you put molecules between them, so these are some kind of molecules, it could be many things, would separate the layers, and we could study the layers, the graphene layers, individual ones, and then the molecules, how they were affected by sitting in there. So that was kind of a work that took about, well, I was involved with this for 15 years. So we didn't work so fast those years as we do nowadays, I suppose. But there were many graduate students that, and I wish you had done the statistics and told me how many graduate students were in that period. So that's a homework problem. So we put materials that gave electrons to the graphene, and then we had materials that took electrons away. We had both kinds, and so the alkali metal intercalation, so this is rubidium, went between the layers. So rubidium has one free electron per atom, so we had those electrons could wander into the carbon system. So that's the idea with that. And here are molecules that sit between the layers. And so these are bromine molecules. They stay in molecular form, but we can measure how they get changed by measuring some property. For example, the lattice vibration of two bromine atoms in the molecule changes by about 50% when you put them between these layers. It's amazing that you should have such a big interaction and the molecule still stays together. That's one of the wonders of chemistry, that things like that can happen. And we were able to measure the spectrum here for many orders. As you could see, there were harmonics in the vibrations. So moving fast forward, now I'm moving into the 1980s. So in this period, I had the idea and put a student working. What happens if you have a surface and a laser comes in and hits the surface? Well, we're going to put quite a bit of energy into the laser, so it does something to the surface. And what it did is it pulled out little carbon clusters, and I expected it would be C2, C3, C4, like that. And it did exactly that if they weren't too energetic. When they got a little bit more energetic, it pulled out big chunks, and we could tell that because our clothes got all sooty. So we knew that something funny was happening, and it gave us the idea to measure. So here's a stick of carbon, and you have a laser coming into the front. I'm not going to point this on you, don't worry. And it comes out like that. But along with what comes out like that were big chunks of things, and we could measure how much material vaporized with how much energy went in. And from that, we could figure out that we had something on the order of C100, very big chunks. And we couldn't imagine what was happening, and nobody else could. We went down to Exxon Company, where they were big experts on clusters, thinking that they could give me some advice about what might be going on. And that convinced them to do this experiment. This is a very famous experiment, many citations. So you could see here that this is the size of the cluster. So this would be like 15 atoms in the cluster, 20 atoms in the cluster. That's the idea. And then here, 40 atoms. But you see that the spectrum looks different. Here, every unit is a different cluster. And here, the units are only even numbers. So something's going on. Couldn't figure out what was going on. But the most interesting thing was what Smalley at Rice University noticed, that the peak for 60 and the peak for 70 were bigger than all the other peaks. So what was happening? And that was, of course, the discovery of the fullerenes. So when the fullerenes were discovered, so that was a very big molecule. It seemed like man-made. Actually, they found it in space also. It wasn't totally man-made, but it was studied in great depth. This attracted hundreds of people on that diagram I showed before. This really got people interested in carbon. And I think it's chemists in particular because it was an interesting molecule. And it was a beautiful molecule, so symmetric so lots of people were interested. So now, in my own career, I'm moving fast into the next decade. So now I'm 1990. That was 1980, so I was doing fullerene. In 1990, catastrophe struck to me. So I had been working on high magnetic fields from 1960 to 1990, and that was my research field. And right across the street from the main building in MIT was the magnet lab. And that's where I had a lab, and I had all my students there studying high magnetic field. But the magnet lab moved to Florida, and I didn't move to Florida with the magnet lab. So I had to change fields dramatically. So there was an interlude. I was trying to figure out what to do. Now, people sometimes are discouraged when they go into some professor, they want to do their thesis with somebody and they get turned down. Professor says, oh, I'm too busy, I don't have time for you, or you're not good enough, and so on. And so you get very discouraged. Well, sometimes it's good to be shaken up. So I tried a whole bunch of things. So first I started fast optics. I got into that. Eric Ippen was in our department, and he wanted to study carbon. And he asked me if I could help him. So we got into a collaboration, and we started studying coherent phonon generation in carbon. That turned out to be a really interesting problem, and I could have stayed in this field probably. We sort of observed spectra like this. We have these oscillations that gave information about what happens to the dissipation of energy within the molecule. This is a very interesting topic, as you can see over there, and you can study line widths, lifetimes, and all that sort of thing. But I didn't really know what I wanted to do, so I tried a bunch of other things. And so one of the other things was studying carbon fibers. That was sort of motivated by industrial interest in carbon. There's a big industry, not so big, but moderate-sized industry in Japan, not too much in the U.S. So I had a collaborator, Endo Sensei, and so we were doing this project together. So that's this thing. And we wrote a book, and I had a lot to do. Even Sensei didn't participate in the book, but we got a bunch of people from the Department of Defense. They needed to have something for you know that carbon fibers made the space program possible. So there was a lot of federal interest in this, and the people that were trying to make things based on carbon fibers had trouble understanding the literature. It was very hard to read. So we wrote this book. So, okay, so I became an expert on carbon fibers for 10 years, and so this is the product. And, but the government was interested in carbon all of a sudden, and they invited Smalley to this conference to talk about C60, and they invited me to talk about carbon fibers. And so somebody asked the question. We had an audience that, not this big, maybe a quarter the size, from different military agencies, people working in government and so forth. And so somebody asked, what's the connection between C60 and carbon fibers? Well, we didn't really know, but this is Gedanken experiment. So you go C60, C7, just elongate it, and eventually maybe you can make something that was a single wall carbon fiber. Well, you know, that was a pretty interesting idea. But so at least I came back to MIT. And so this was the summertime. And in the fall, new people come to the lab, and they're looking for problems. So we had these two Japanese people who showed up. I think I probably have it on the next view graph. Yep. So Saito Sensei, he's now Sensei, of course. At that time he was a young guy, and Fujita, two just beginning, just emerging faculty members, just starting their careers, and they were looking around for problems, and so they got fellowships to spend a year at MIT, and so they both arrived. They didn't know each other. They arrived and they were looking for problems. So I said, you know what? We have this idea that suppose you could make a nanotube that I just showed that just had one atom thick. Would that be interesting? Should we try to make such a thing? It's not interesting. We won't put all the effort, but maybe it's interesting. So we did a theoretical work, and so I was involved with this. And so the idea is you take a sheet, a single layer, and you roll it up to make a tube, one layer thick. What would the properties be? So this was known already because this is the electronic structure. And when we bring this thing together to make something like this, we get cones. Everybody knows that because that's graphene. So this is very popular. But the idea about this is that if you are making something like this and you have only a few atoms, you have only a few quantum states. So if you have 10 atoms, you have 10 quantum states. So you have to have 10 cutting lines to make 10 quantum states. It's simple like that. And so the idea is if one of these cutting lines goes through this apex, it's shared by the valence and conduction band. And so you have a metallic state. And if that doesn't happen, if the cutting lines don't happen to go through the apex, then you have a semiconductor because there are no states at the apex. So there has to be a band gap. So we wrote a paper. So that's 1992. APL, Applied Physics Letters. Maybe not a fancy journal. We just send it off. It was short paper, so we send it off there. Well-cited paper. And it predicted that you could have metallic and semiconducting tubes depending on geometry. It was a really revolutionary idea, and people didn't believe it. So I used to get invited to give talks because people wanted to hear about it, and then they wanted to shoot me down. So, and Fujita, he died very, very soon after this paper. He was a very young man, but he had a heart attack. And Saito was in Japan, far away. And so I got the pleasure of trying to answer the question of semiconducting and metallic tubes. It took 6 years before anybody proved this in the laboratory. I guess science has moved as fast then as it does now. You have a paper like that now with a lot of citations. There would be a lot of people working really hard to try to make. Anyway, 6 years later, it was demonstrated by 2 different groups independently, and they both got the same answer. Yes, this is correct. Then the field took off, and everybody in this room practically has heard about semiconducting and metallic nanotubes, so this is well known now. But it wasn't at the time, and we had this simple, very simple theory, but it took a while to get going. The first spectroscopic studies actually was done on a sample that had 1% nanotubes in a carbon material. And we could see a signal. It was very, very poor. And the people in the journals didn't like it, but we did get it published in 1994. But it didn't really make much news. The data was really poor. But in 1997, we benefited from the first separation by chemists. So Smalley was the same guy with the fullerenes, was the one who made the first samples. And he was very happy to give us a piece of sample that we can do this experiment. And this is the result. So he's also co-author on this paper. And so it shows that the effect is resonant, as I showed in the previous view graph with the electron density states with the different peaks. And so depending on the photon energy that excites the electron from the valence conduction band, you see that this vibration, that's this breathing mode, optical breathing mode, looks very different for different excitations. It has a little different frequency, different line shapes, and so forth. And that's because of the different metallicity of the samples. So, and then we discovered the radial breathing mode that we use now to measure the diameter of nanotubes. Well, there are many more ways to do that now, but this is the first one that was known. So, and that's shown here. So this was kind of a landmark paper. And Peter Eklund was the main professor on this, and A.M. Rao was the graduate student who did this work. It's nice to have papers for your thesis that get landmark attention. Sometimes you're lucky. So the signal was so strong that we had the idea back at MIT that maybe we could see a signal from just a single individual nanotube. And so we tried that very soon thereafter. And this is a sample made by Charlie Lieber at Harvard. We had to have a chemist to help us because we couldn't have made the sample ourselves. So here are the individual tubes. You can pick out one of these in the spectrum on this. This is You can get a light beam here. That's the way we do the experiment. And then we found that different tubes, the metallic and semiconductors, have different looking spectra. So, and this sort of became a landmark paper because you could, just from the spectrum, you could find out what the chirality of the tubes, metallicity and chirality of the tubes. So that means how the hexagons are oriented on the tube. That's what the idea is in simple language. So this is 2001, and this was the beginning of single thing spectroscopy, single molecule for this and that. So this was done for Raman, but you do it for photoluminescence and all optical properties. And there's some company around here that's interested in double wall nanotubes. I heard we had presentations today of local work, so we work in that as well. And one of the interests on that is that, oops, I didn't mean to do that. Let me go back here. The chirality of the inner and outer tube can be anything. Well, I mean, you have to have the right separation, but there are many choices. And you can move them in and out. You can move them this way, and you can move them this way, twist. So there are many, many ways that you could arrange this so that the spectrum actually looks kind of different. And just from the point of view of metallicity, you can have 4 different flavors, semiconductor and metallic. You combine them any kind of way. 4 flavors are shown here, but then you can move them in and out all many ways. So you can have a really high variety of spectra. And this gave the idea of taking 2 sheets and misorienting them. And that's currently a big topic in graphene. And so we learn a lot from studying graphene, and that's an interrelated subject. I'm going to get to graphene in just a moment. But here's how beautiful people can make nanotubes. So you see double wall nanotubes, and there's an array. They're all double wall there, and they have almost the same diameter. It's kind of amazing what the chemists can do nowadays with materials. Yeah, and they're telling me to move faster. So here you see double wall and triple wall nanotubes, and we studied triple wall nanotubes. And we could study the individual components in the triple wall nanotubes. I have a student actually in Germany doing a thesis on this. So we work worldwide. We pick them up. They're interested in doing something, so we do some. So there are 8 flavors here. Okay, so this gives you an idea. Now I'll make some comments on graphene and then wind up. So graphene, of course, was known back in 1947 with first theory of graphene paper, what the electronic structure of one layer. The paper is 1947. So we've known about it for a long time, and it was an inspiration. But there wasn't much thought about studying graphene single layer for a long, long time. And the pioneering work was done at Manchester in the UK, Guy and Novosela, graduate student. So that's 2004, that's where the marker is. But we kind of knew about it, but we weren't studying it. So Böhm, Hans-Peter Böhm, that's his paper in 1962. And he has a series of papers at that time, and then he stopped working on it. He just didn't continue. So sometimes you come on something, a hot topic, and you don't recognize it. But he's followed the work, and he's still alive, and same age as I am. And we correspond. We know each other from a long time ago. So single layer and double layer, I thought I'd show this to you because they're very different, but they're very similar. If you look at the electronic structure over the whole zone, gluon zone, reciprocal space, they look almost the same, right? But if you look at the K point, where the action is, where the Fermi level is, the Fermi level goes through the 0 point. For the single layer, you have a linear E versus K. And for the bilayer, it's quadratic. And that makes the electronic structure properties very, very different. It looks almost the same, but the properties happen to be very, very different. And this shows you the Fermi surface. You could see how that is. So this is the Scotch tape trick of Manchester, what they taught us. And so these are the pieces of graphene. They look pretty terrible. But if you look at them on short range under the microscope, they look much more beautiful, as I'm going to show you. So now that's more and more magnification, and this is now 200 magnification, and you can begin to see single layer different from bilayer, as you can see on your right. And so this is the frequency in the samples of this particular paper, and here's some more pictures of the monolayer, bilayer, and beyond that. So amazing properties. The thinnest material is very strong. The bonding of carbon-carbon bond is the strongest bond in nature, so that you can make very strong materials, but yet they're flexible. So that's very, very nice. The carriers have very high mobilities, and they're wonderful heat conductors. All this is known for a long time, but not exploited very much until very recently. So there are many open ends here for people to work on, because this is both old and new. It's known for a long time, but not researched much until very recently. The sister to carbon, graphene, is boron nitride. B is column 3, N is column 5, carbon is column 4. So Bn is a sort of combination of the two, and the lattice constant in boron nitride is almost identical with that of graphene. So it has many interesting properties, and when you make a layered compound, it's very flat, as shown in this view graph here on the left, compared to the SiO2. We like SiO2. That's the mother of the semiconductor industry, so we have to work with that, and we love it. But you see it's kind of a rough surface. So for science, BN is interesting, and for practical applications, SiO2 is interesting. The spectroscopically, graphene is very, very unusual. Spectra, normally, first order spectra are strong, second order spectra are weaker, third order spectra are very, very weak. So, however, here, because linear E versus K, you have amazing things happen. That the first order spectrum, which is shown here, is this monolayer graphene. It's of certain size, and the second order effect, which should be, it's done in perturbation theory, so it should be small, right? But it isn't small. And it isn't small because you have resonance states in every single component of the second order process. So when you have all these three resonances, you get the combined effect is huge. So that's why this is such an unusual and interesting material. Another interesting aspect about it is that when you excite an electron into the conduction band, it can stay there for a very long time before relaxing. So you can get a population inversion very, very easily. There's not much been done on utilizing this population inversion in practical applications. For one thing, people didn't know about it too much, except for some pundits, but it's not widely known. But I think that might be an area for thesis work or companies or something. And you can make many layers, and each layer has interesting properties. So we have been studying this reference. We still work on that. And some of the interesting things that happen with that is that we can study all the different combination modes. And they occur here. There are little tiny wiggles here, but they have interesting symmetry properties. And if you vary the Fermi level by changing the laser energy, something like that, and changing the doping levels, then you can do many things and study those combination modes. And that's what we're doing at the present time. That's one of our research areas. Yeah, the spectra doesn't look so great, but if you persist and take many traces, then you get nicer lines. Finally, in this area, I'll talk about ribbons. So, graphene sheet, infinite, right? But we can make something that's like a nanotube. So imagine that you take a nanotube and you open it out. So that makes a ribbon, right? So the basic components, you can have an edge that looks like this. We call this a zigzag edge. And then we can have an edge that looks like this. We call this an armchair edge. You'll see there are 5 rows of atoms in both cases. Turns out that theory tells us that both of these are metallic. But the metallic states are very different in the two cases. So I had a young lady that was doing her thesis in Japan, and she wanted to see how it was to be a female in the United States. So she spent a half a year doing her thesis, part of her thesis with me at MIT. And we got into this work. So this is a paper that we wrote, very, very heavily cited paper. And so she was doing a theory thesis. And so we were studying, you have these different ribbons of different, I showed you 5. You have 4 layers, 4 rows, you have 5 rows, 6 rows, and that's what's shown here for the armchair orientation, and this one for the zigzag. And you see for a zigzag, no matter what the ribbon width, it always has a high density of states at the Fermi level, so it's always metallic. All the zigzag ribbons are metallic. But the armchair, we have a choice. We can have a metallic case, like n equals 5, but then we can have semiconductors, n equals 4 and n equals 6. So this is very much like nanotubes. We have semiconducting, metallic, and the same frequency of occurrence. So we use this to do some spectroscopy and transport measurements, and just to show you that we can tell with a laser. So the laser has a size, wavelength of about a micron, roughly. And we're looking at edges here where I'm going to show you, you can see the atoms. And we get information about what's happening at the atomic scale, even though we're looking with a probe that's very big. And that's because if you understand what the physics is, what we're looking for is when we look at the zigzag edge, we're looking for this high density of states. And we're looking at the armchair edge, we're looking to see if they're semiconducting or metallic. And they have different spectra. But they would have different transport properties too. So, all of these things all go together. And so now I'm going to show you finally what we do with these edges to make them beautiful. And this is another student, this is a student's thesis. So we asked ourselves, suppose we did the transport measurement inside a microscope. Microscopes, TEM microscopes, allow you to put little gadgets inside. So we have a very simple gadget that looks like shown here that will measure transport, to measure IV characteristics. It doesn't measure too much, but IV characteristics it does. And then we could put 2 electrodes. So we have a STM chip here, and then we have a sample holder. So this is ground, and this is voltage. So put a voltage across here, and you get a current. And we send the current through the ribbon, and the ribbon looks like this. The ribbon is sort of a messy little thing, and it has about 20 layers of graphene. It's not a single layer. It has a few layers. And that was made by another student, not the student that did this, a different student. So you start out, the IV characteristic starts out linear, and then you get above 1 volt applications. 1 volt isn't very high. It gets nonlinear, more and more nonlinear, and then it just shoots up like crazy here. And when you get into this regime, you start annealing the sample. the sample goes up to about 2,000 degrees centigrade, and we get something that looks like this. So this is the original material, and I showed you we have electrodes across a piece of this. And this is when it shoots up, the current IV characteristics. So this is seen in an ordinary, not a fancy, just an ordinary TEM. This is done in a student instrument that's used for the lab course. So it's not very fancy. But the result is interesting. You can pick out just from visualization what the armchair and zigzag edges. So this is recent paper, Science magazine or something like that. And then people ask us, well, what temperature are you? Well, we had no idea, so we put little platinum particles. They melted about 2,000 degrees centigrade, and we could watch them melt. So that gives you an idea of, not very accurate, but an idea of what the temperature is. And it also raises the point that we need to do some metrology to get good sensors for temperature measurement at 2,000 degrees. We don't really have them. So, and you can see here what happens. You get accretion, so that some of the little particles get bigger and others evaporate. And you have to do the balance of those two processes to figure out what the temperature. That's what we're doing with this, but it's not very good or very accurate. So this is what happens after different time lengths. That's the kind of data we use. So I'm going to end my talk now. And so 50 years of carbon research, I was telling you. Started out studying carbon, cells, graphite. That's all we knew at the time. Then we had the idea maybe we could study an individual layer by putting something else in there. So we had interpolation compounds. And then we had carbon molecules, studying spectra and other things about it, writing a book about it. And then nanotubes came along, and then graphene came along. And so what's next? So, really don't know, but so here are a couple of things that current work, mostly not published. So this was inspired by some work for some of our collaborators. So look at this. This is a lineup of nanotubes, all about the same size. They're not exactly the same size, not the same plurality, but similar. And now we're going to put an electrode across them. And so you're going to see that in the presence of the microscope, you have radiation and something happens, something gets hot, and two of them merge. So this was observed. And we've done quite a lot of experiments with the merging. And every time we see this happens, we have a certain Raman peak that shows up. It has to do with a linear chain. So we know that that linear chain is involved with this, but we don't know exactly how. Because all these different emerging experiments, and we have more merging, we have a lot of merging experiments now, we always see that particular spectral line. But we don't understand the connection. So that's work to be done. And this is kind of the merging thing. And what we're studying now is the whole concept of making new carbon nanostructures based on some nanostructures. So we start with nanostructure A, and we do something to it, and we get nanostructure B. So that's our present work in this. And it's amazing that such a thing can happen, and we don't understand exactly what's involved. We think this linear chain thing has something to do with it, because we see it all the time when this process occurs, but we don't understand why we see it and what is happening in detail. So we need more work in that. And the other thing that we're working on are fellow layered compounds. So MOS2 and bismuth telluride, these are layered compounds that are interesting in material science for different things. So MOS2 is a big lubricant. commercial lubricant, very popular for that. But it also, single layer is fluorescent, so you get a spectrum from it. But when you have 2 layers, that doesn't happen, just 1 layer. So interesting things with it. Bismuth telluride, shown is a thermoelectric topological insulator. It has different interesting current properties, but it's a layered compound. So nowadays, instead of having single layers, we have cluster layers. As you can see. MOS2 is 3 layers, so 2 S layers, and then the M layer, MO moly layer in between. Moly disulfide and then moly diselenide, and there are a whole family of those things. And then the bismuth tellurides are even more complicated. They have five layers. But there's a whole family of transition metal dichalcogenides of different sorts that are interesting for these kind of applications. Not too much work yet done on them. This could be an interesting area for something. We don't know exactly what the something is. The challenge of the unknown. So that's where I'm going to leave you. So I just say that other fields have a similar trajectory. Not all fields, but I've been working in the area of thermoelectrics, and we can draw a very similar curve. That very little work until the early 1990s, and then something happened around 1990. It wasn't only the magnet lab disappearing, but many things happened all of a sudden. And what?
That's where the new magnet lab appeared.
Yeah, well, maybe it's the new magnet lab that had to do with this. We can ask Professor Schwartz to comment on that. He knows something about that. Well, I just leave you with that and have questions.